Let's have a glass with a lid, or I have closed it so that water or water vapor, whatever we are going to discuss, will not escape anywhere. We keep in this video. Okay, so let's first understand water molecules. These are water molecules. Why they are stuck with each other? Why they are not leaving each other? Because they have intermolecular forces. Intermolecular forces. First, understand that. Okay, so this guy is binded by this guy with some force. So this guy also is binded by this, and likewise. That's why they are stuck together. They are in the group. And why that is happening? Because we have kept this glass at 25 degrees centigrade. That is like room temperature, I can say. This is a room temperature, say. So I'm talking about this room temperature. So what this temperature does, it relates to the kinetic energy, the average kinetic energy of all the molecules. Because see, at the room temperature, not every molecule will have the same kinetic energy. So this guy over here can have a different kinetic energy. This can have a different kinetic energy. When I'm talking about kinetic energy, you can think of speed, right? Think of like speed. So this molecule may be, going around like the highest speed, and this is very lazy, it is just going like that. So that can happen. But if we take the average out of it, that is what we are calling the temperature. Temperature is nothing but the average kinetic energy of this molecule. So whatever the kinetic energy average they have, that's what the temperature signifies. As if now let's keep things cool, calm, relax, chill, and have at room temperature. In room temperature, is it like nothing is happening? Let's see. So these molecules, and I'll be talking only about focusing on only on the surface molecules. So these are my surface molecules. So as I've told, they will also have some kinetic energy. All of these molecules will have some kinetic energy, right? But will they have same? No, this is the average one we have taken, right? At this temperature, they will have like somebody will be very fast, very energetic with the higher speed, and someone will be very lazy. And they can also distribute their energy by hitting with each other, right? This guy was very energetic, but when it met this guy, it was very slow, so it also slows down. So that is happening at 25 degrees centigrade. But when we are talking about average, so there will be some molecules which will be having higher kinetic energy, right? So like take an example, like if you take average of marks, right, in your class, let's say of physics subject or chemistry subject, so there'll be students who will be above average, right? So they will having more marks. Or we can say similar example, like these molecules will not have same energy. Some will have higher kinetic energy and some will have lower kinetic energy. But what about those guys who are having higher kinetic energy? So they'll be able to break these intermolecular forces and go here in a gaseous state, right, in a vapor state. So maybe this was the higher, very higher energy and broke the bond and went up like that. And that is what we got. First vapor, right? First vapor molecule. So this molecule of water has become a vapor now, right? It has gone beyond, it broke the bonds, intermolecular bonds, and went into that because it had kinetic energy. The reason can be, two guys hit it, with a higher kinetic energy, so it got that energy and went up, anything like that. So it is all happening random. This process, which we are discussing, we call it very fancy name, evaporation. Yeah. So what we are seeing here is evaporation. The liquid state is getting into gaseous state. And why that is happening? Because some of the molecules on the surface will have higher kinetic energy. They will break these bonds and go up. And that's why they will create a vapor. Evaporate. They will evaporate. Yeah. So that is happening. Now let's see, maybe not only one molecule. Let's say this guy also. This guy also got kinetic energy higher and it also went up. So this guy also got into the vapor state, right? And now this will continue. So this will go on evaporating, and let's say our molecules, gaseous molecules or vapor, are getting collected here, right? And remember, they are having higher kinetic energy, right? They are having higher kinetic energy. So they are not lazy like them, right? They have higher kinetic energy, so they'll be going around here like gases go, right? Very fast, higher speeds, right? They are going around hitting these corners of the lead, trying to come out, and that's what they are doing, right? Not like water. So now we have collected so many, evaporation has happened, many molecules have come into the vapor state. And now what will happen? See, these molecules, which are in now vapor state, will also have kinetic energy, right? So they can also now, because they are getting collected, the space is getting lesser and lesser, they can also hit other molecule, right? Which was at higher speed, and they may cancel each other, right? They can decrease others' kinetic energy, or it can happen this molecule can hit this water surface. So water surface is at lower kinetic energy than this guy, so it can lose its kinetic energy. So what can happen? This molecule can go back. This molecule can go back to the liquid state. And what this downward arrows I'm showing? Oh, sir, now this opposite process is happening, and we call it fancy name. Condensation have started, sir. Condensation. Yeah. So liquid molecule having kinetic energy going into the vapor state, we are calling that phenomena evaporation. When the higher kinetic energy molecules are getting lower energy, they are coming back to liquid phase. We are calling that condensation. Okay. So as of now, can you say who's winning? Evaporation winning or the condensation winning? So let's say in every second, okay. So let's think about a rate. Every second, two molecules are going into the evaporation state. In every seconds, now one molecule is getting condensated. So who's winning? So if you say every second, sir, one more molecule will be net added to this, right? So because one will be going up, but one is also coming down. But there is another one, right? For evaporation is rate is more, right? But this will happen when this get stuffed with vapor. One molecule is getting added here. Okay, let take the analogy again. I'm thinking about 1 second. So two molecules per second are going into the evaporation, but the condensation as if now is happening with one molecule at a time getting liquefied or condensed. So this guy is winning. That's why one net molecule per second will be going up. And now they are filling the space. Can you see? They are creating some pressure, right? They are creating some pressure here. Now, due to this crowdedness, what will happen? More molecules will hit with each other or they can hit the surface, and one more molecule can come down and get liquefied every second. Now, if you observe carefully, in every second, two molecules are getting evaporated and two molecules are condensated. So they are like equal. Or we will say we have reached equilibrium state. We have reached equilibrium state. And this is not a static photo. This will go on happening. The evaporation will still continue. The condensation will also continue. But what is happening that the rate is same, right? So equilibrium state, what is the definition? Rate of evaporation will be equal to rate of condensation. And when this stage has reached, when equilibrium has reached, there'll be some vapors here, right? And they will create some pressure, right? On the surface, on the lid, they are creating some pressure, right? Around on the surface layer. And this is called our topic name, vapor pressure. So let us summarize. We have talked about the vapor pressure. Vapor pressure will be always talked at certain temperature. Here we have talked about 25 degrees centigrade, the room temperature. What will be the vapor pressure? That vapor pressure is the pressure of the vapor calculated when the equilibrium state has reached, or rate of evaporation and rate of condensation is equal. Let's play with this temperature now. What if I lower it to 10 degrees centigrade? So lower temperature means lower energy of these water molecules. So very few of them will be evaporated because they will have a lesser chance of getting higher kinetic energy. So instead of two as it were going, maybe only one will evaporate. Condensation will start when one molecule will come back. But will you see so many vapors here? No, the evaporation is less. The kinetic energy is less at the lower temperature. So you will see lesser molecules. So let me decrease this number of molecules in the vapor. Yeah, so these molecules will not be there, right? Like that, right? So this is not one is going, not two are going into the vapor state. The rate is like one molecule per second going into the vapor state. The condensation is also started happening, but look at the vapors. Vapors are less. So less vapor pressure. So the water at the lower temperature will have a lower vapor pressure because there are not so much molecules which are getting converted into the vapor state. Now let's play again, but now I will do a different thing. I will increase the temperature. Let's say I have doubled it, like I have doubled the temperature to 50 degrees centigrade. What will happen? Right? So the rate of evaporation will be more because they have more kinetic energy. There are more chances of molecules from the surface going into the vapor state. So they can go 4 here per second, right? 4 molecule can go into this. So the vapor will be collected more here, right? Till this equilibrium state reaches, right? There will be more densely packed here. They will create more pressure, right? So 1, condensation starts, 2 and 3, and let's say more molecules are still getting added, and finally 4. equilibrium state have reached. But look how many vapors I have. They will create more pressure on the surface, on the side walls. So at the higher temperature, more vapor pressure. Because to reach this equilibrium state, right, it will take time, and in that time there will be much of vapor getting collected here, which will be exerting more pressure now.